Hi, I'm Andrew Cagney, and I'm here to talk about Libreswan. This talk is part of BSDCan 2020. This year, obvious reasons, it's all gone virtual. So what are we going to look at? First, Libreswan, what is it? It's an IKE daemon, an Internet Key Exchange daemon. And then, why is it of interest to NetBSD, the BSD community more broadly? So let's get down. So, first of all, what is and why use an Internet Key Exchange daemon? Let's do an example using Libreswan. What about a problem? Let's go with 3. Problem 1. You have 2 endpoints and you want to make sure that all the traffic between the 2 endpoints is encrypted. No ifs, no buts. Any traffic going between those 2, encrypt it. That's called transport mode. The next problem is a bit more complicated. It's where you have, say a corporation, and they have 2 routers on the internet. They don't want to pay expensive private landlines, if you can even get them nowadays. And for them, they will have 2 gateways, and the gateways will take all the internal traffic and tunnel it through to the other end, where it will get decrypted, and then it can flow around again. Of course, any sane corporations also running SSL, everything else. It's another layer of security. Finally, it's problem 3. It's where you have a home, and you have a router as they say it in this country, and you have TCP or UDP as the only protocol you can get through to the other end, where you want to reach your protected endpoint. TCP, yeah. Some people can only get TCP through from their home, or wherever they are, and get it to where they want to be. So it's come up, and Libreswan supports it. Maybe not the BSD kernels, but we're hoping. So let's set up an example here. Let's using setkey, which is what NetBSD comes with, the same with all the other BSDs. You can use setkey to just set up the IPsec tunnel or transport connection, brute force. So here we specify the 2 endpoints. We specify it should use ESP, which is encapsulate and protect the traffic. We specify the algorithm, looking a bit old. Specify the keys, and then we specify SPD add, what exactly is going to get tunneled. And in this case, it uses transport mode. Very error prone, not good for maintaining. You get things like NIST rearing their head and saying, okay, your corporation, you're going to change your keys every 8 hours. Even more frequently if, you got a lot of traffic going through, not 1 or 2 bytes. And so you're not going to be doing that by talking to your mate on the phone. So enter the Internet Key Exchange daemon. It deals with all the mess and the frustration, although I'd add some as well, of establishing 2 IPsec endpoints. It first establishes its own tunnel, secure connection, and then it uses that to establish the IPsec tunnel proper. And does, and also IKE v2 doesn't suffer from the travesties of IKE v1. Something to keep in mind. If people disparage IKE, probably talking about IKE v1. So, let's install an IKE v2 daemon. What do? I'm going to download and install Libreswan. First, just so that anyone's wondering, here's where it's going to put itself by default. User local. Someone wants to bundle up for package source. We figure, stay out of their way. This way you can have a developer version, and if someone bundles it, stays well clear of it. However, it does put its PID in, logs in var log and PID in var run, and it does install rc.d. So I can use that as well if you want to set it up to start up when you boot the machine. So, all very straightforward. Use pigeon, however you pronounce it. Install the dependencies, clone the Git repo. Currently the BSDCan's only a mainline. Build it, install it. Done. And then finally, start up Libreswan. You can use the IPsec command, or you can use var rc Pluto. Same thing. It'll start it up and make sure it's all set up. Then you do a status just to check it's running. That'll give you a stream full to chew over, so it's not here. Configuring Libreswan. Thing to know about Libreswan is one of its models is that the ipsec.conf file can be used for both ends of a connection. You might have your left, you might have your right, and that same file can be shuffled back and forth. Of course, it doesn't contain keys or anything that's stored elsewhere. And so when you go looking at a Libreswan config file, same as StrongSwan, you'll find it refers to left and right. The thing to look for is the left equals and the right equals. That pins down or orients the configuration. And so here, left is 192.1.2.46. That lines up with the ifconfig the interface is going to use. And so everything else in that config file is tied to left, and it assumes the other end is right. Bit of an interesting one, but that's the way it works. So, first thing we do, once we've got our Libreswan running, is we do an we add this particular configuration. It's called transport because I chose that name. It could be called anything. And do an auto up. Just to go quickly through the config, we specify left ID and right ID. These are entries in use like etc ipsec.secret, so this is still using a pre-shared key. It's not trying to do certificates. That's another battle for not for here. Specifies the authentication. Like I said, it's using a secret, the type of connection, transport, and here I've told it to use AES and SHA-1 for the ESP connection. For IKE, it will just use defaults. They're pretty sane defaults, very conservative. We'll see them later. So once the connection is established, always a good idea to check it's doing stuff. And yep, sure enough, TCP dump shows that ESP traffic is flowing between these two endpoints. Life is good. So part 2, why Libreswan, why IKE v2? So, why IKE v2? It's a far simpler protocol than IKE v1. Like I said, you look for disparaging comments about IKE v1, that's easy to find. IKE v2, far simpler, far more understandable. I mean, I've read the IKE v2 spec. There's only one RFC. IKE v1, there's this plethora of RFCs and you're never sure if you're reading the right one. It's had extensions and it's addressed limitations of IKE v1. UDP tunneling actually works. They've extended it to TCP. It supports AEAD, authenticated encryption, the AES GCM algorithms where the encryption and the authentication occur in a single pass, more efficient algorithms. Modern CPUs use those, and it can use those for IKE. It does fragmentation right. Again, IKE v1, yeah, maybe not. And it's been extended with things like post-quantum keys, and as new algorithms turn up, they're quickly integrated into the RFCs and added. Of course, things need work on a BSD. There's a feature called opportunistic encryption. That's where an outgoing packet triggers the IKE daemon to go and establish an encrypted channel, and then with encrypted channel up, traffic can flow. So it's all done on demand and you can establish a connection with any peer out there. The authentication's done using secured DNS records, so you're pretty sure you're talking who you think you are and you have a channel that's encrypted. Like I mentioned, TCP tunneling, because sometimes you just have to. And finally, things like mobile IKE, mobile phones roaming between the Wi-Fi and the one mobile provider, another mobile provider. You don't want your IPsec tunnel going down just because that's happened. Why Libreswan and on NetBSD? Well, here's your mandatory comparison chart. I've got the ones I've come up with are Raccoon, Raccoon 2, StrongSwan, OpenIKED, Libreswan. All the ones that don't actually run on NetBSD probably can be got to, so that's not really a reason. But when you start to look a bit deeper, you do start to find some differences. Crypto library, Libreswan uses NSS. The others use SSL. You want diversity. You want to cover things from, OpenSSL runs into trouble, you have Libreswan. NSS. NSS runs into trouble, OpenSSL. Cover yourself. Next one is FIPS tested. Bit unusual, but it's a good indicator of how the code base is going. If someone gets FIPS certification, they've probably done some work on the code base to clean up how it manages and handles algorithms. Because FIPS testing involves running a test suite against the crypto algorithms used when you're doing all this negotiation. More interesting and more recent, where is the FIPS boundary? So in Libreswan, it's now purely uses NSS for its crypto. It has no built-in or internal algorithms. So its FIPS boundary is NSS. When you go to get a FIPS certification, you just certify NSS. No need to try and get Libreswan as well. Much simpler, good indicator that people have been doing work on cleaning up the cryptography side of things. Test frameworks. So StrongSwan, Libreswan use KVM. More recently, Libreswan's using namespaces. Same tests, just they're run on Linux namespaces, purely for speed. Limitations, but good speed. The last one is trying to keep track of RFCs. And there, StrongSwan, Libreswan, I'll give them a yes. OpenID, I think it is, but it's kind of hard to tell. Because I noticed it only recently seemed to add BSDCan. But I think it's progress there. Again, your horses for courses. So, now, part 3, let's have a little bit more of a look at IKE v2. So, what does it take for an IKE v2 daemon to establish first a cryptographic channel between the two IKE daemons, and then a cryptographic channel, and then the IPsec channel beneath that. So it's a parent and there's a child. Not like IKE v1. So to do it, there are two exchanges. The first is the IKE SA-NET exchange. This sets up the tunnel between the two endpoints and it secures it using Diffie-Hellman. Straightforward, nothing unusual there. Then there's the IKE-auth exchange. This is to establish trust. You have a secure tunnel between two things, but you don't trust the other end. The IKE-auth exchange proves to the two ends that, yeah, this is really who you want to be talking to. And piggybacked on that exchange is enough information to set up an initial child SA or an IPsec tunnel transport. So let's go through the first exchange. First thing off, the initiator generates this Diffie-Hellman keying material, sends it off to the responder, and it throws in the following. It throws in an SPI, some sort of unique identifier. It throws in your nuance. That has to be random. SPI, it turns out, doesn't have to be. Nuance does. It throws in a sequence number. Nuance and sequence number to stop replay attacks. Someone forgot that in an earlier version. Proposed cryptographic algorithms for the IKE SA, it's a list, what encryption, what the integrity will be, how you're going to do key expansion using pseudo-random function, and the Diffie-Hellman group you're going to use. And finally, there's the keying material generated earlier. So off it goes. Then the responder gets this in, takes a look at it, looks at these suggested cryptographic suites and picks one from the big long list. It computes its own Diffie-Hellman keying material and then sends all that back. And at the same time it throws in its own SPI, its own responder SPI. So you now got two ends between the pair uniquely identified. Does the nuance, does a sequence ID, that chosen crypto algorithm, and of course that keying material. The initiator gets this. Now it has enough information to set up. Well, first it looks at what came back and it says, hey, yeah, I do like what they proposed as the final algorithm. It's not silly, it's not la-la land. And then it completes this Diffie-Hellman calculation. Meanwhile, presumably the responder's probably off doing the same thing. So at this point, there's a secure channel between two endpoints. They don't trust each other. What happens next is the Diffie-Hellman secret. It gets expanded. So you're now gone from some information to a huge amount of information, and using that expanded information, the expanded random number, you can pull out all the keying material you need. Keying material to encrypt in both directions, keying material to verify integrity, so on and so forth, and eventually keying material to use to establish the initial child. So now the initiator, using the secure information, it sends out it and the responder's SPI, the sequence ID. This is now packet 1, and then all bundled up and encrypted, enough information to do a proof of identity, the IME, because I know this and no one else does, nuance being part of that, various other things. The child then, in addition, if he wants to establish a child, information such as what algorithm the child should use, and other stuff such as IP address, so on and so forth. A basic exchange always has a child, but you're doing more sophisticated things, you can leave it out. And the whole, most of it is secured and tied up and safe. The responder gets that in, checks the packet, it can verify using the information extracted from the Diffie-Hellman exchange. You can verify and say, yeah, this is okay, and if it isn't, drops it like a hot potato. No response, nothing. If you try to set up an IKV2 exchange and things aren't working, you're going to have to go to that responder and you're going to have a look at its logs. You know, this idea of let's be helpful in IKV1 and tell you exactly how broken we are, gone. So decrypts, verifies the packet, and if it feels like if it's in there, it'll create the child, and then it sends back its response. It contains details of the child, and again the responder's proof of identity. Finally, the initiator checks again the secured packet, checks the responder's identity, and if it likes it, it continues on. If it doesn't like it, it should send what's called a delete exchange secured, but we can get away with not doing that, although you're not meant to. So let's have a look at one aspect of IKV2. So IKV2 proposals are made a lot simpler than IKV1. They flattened this data structure. It's just you have a list of proposals, and within a proposal there's a list of algorithms, and you take any combination from that list. You're meant to start at the top and work your way down, find the first thing that can find the first thing you like. So for instance, if we go back to the original IKV1 RFC and get the algorithms out of that, we got DES, 3DES, DES is obviously dead, SHA-1, MD5, it's dead, Tiger, I've got no clue what it even is. And again for integrity, SHA and Tiger and MD5, and then a few mod P groups, so small you can sneeze and figure out what they are. Diffie-Hellman groups, if you want to look at it that way. None of them get used anymore. So things moved on. Libreswan on NetBSD, and using IPsec algpass units, just spits out the algorithms. If you don't say what algorithms you should use, these are the ones it's going to use. ASGCAM, ASCBC, SHA-2, and some pretty strong Diffie-Hellman groups. The DH, mysterious DH numbered ones, they're probably ECP groups. So, and you can see number of different combinations. 96 combination. And the responder goes through that, compares it with what it thinks is actually reasonable, and the responder makes the final decision. These are just suggestions. It's just the responder has to match up something that the initiator said, yeah, I can handle. And so that's it. But let's say you have an initiator that feels like supporting or connecting to anything, and the proposal comes in and it looks like this. This is ASCBC and a lot of other stuff. I don't even know how many, didn't even try and count how many different ways you can expand this. That's a lot of combinations. Funny enough, Libreswan being very old and for years and years only having to deal with 5 algorithms, after all that was in IKV1, didn't handle that so well. It was a tad slow. If you turn logging on, debug logging on, it was a bit slow wading its way through. Oops. Well, fixed in 2016. We tested it, did interrupt testing with Libreswan itself, interrupt testing with old new versions, tried out Strong Swan, everything seemed happy, might have even tested Windows. Life was pretty good. But then, you get this email. Well, as soon as the client starts negotiating like v2 with Libreswan, it blows up and reloads. Probably our fault. Actually my fault, since I did this code. But, yeah, something smells. So, the details were in the response. So, when you accept the response and you send it back, you actually send two things. First, obviously send back the choice, the encryption algorithm, your AES, integrity algorithm, SHA, PRF, and, oh, typo, the Diffie-Hellman, not the group you've chosen, that goes back. And it has to be found in one of the proposals. The other thing you send back is a bit of an optimization. Uh-oh. It sends back which of the proposals this came from. The index was out of bounds. The reason everyone else seemed to work is that no one trusted the index. Libreswan got back to the proposal and went, you know what, I don't trust this. I'm going to totally check it against everything that we sent and make sure it matches one. Because the new code was pretty fast. It's just some constant times the number of proposals sent over. So if someone sends over, sorry, not proposal, total number of algorithms in all the proposals. So if someone sends 20 algorithms over, 20 times some constant. Pretty efficient. And all the others apparently did the same thing, except this vendor. But I'm sure they've done the same thing to us. We keep it happy. So now we get on to part 4. From old to new. What has changed in Libreswan? Libreswan's been around in various forms for a very long time. Okay, let's look at the history. Back in 1995, as best I can tell, John Gilmore started up the FreeSwan project. Now it had two goals. First was to encrypt the internet, and as a consequence of that, and because in 1995 you couldn't actually export crypto, if you're a foreigner like me, you had to go and countries had to go and write their own crypto algorithms. Because you couldn't use Mozilla, so people were writing plugins to get Mozilla to do 128-bit encryption. So it was pretty silly. So Gilmore set out to encrypt the internet, and he's put the project in Canada, where I am now, and try to make that way he could dodge all the US silliness with crypto laws. And things moved on, and by 2003-04 the project was winding down. Technically it was pretty successful, but didn't get as much traction as hoped for. There's a civil wind down, and out of the project came OpenSwan and StrongSwan. They're very civil forks. Then around 2005, best I can figure out, OpenSwan was ported to the BSDs. StrongSwan, I assume, picked up the code, because at that point it hasn't really diverged. And things progressed. Libreswan kind of focused on the Linuxes. StrongSwan focused more on rewriting everything. In 2012, the OpenSwan team ran into a second crisis, and it ended up with a further fork. Something about the easiest way to deal with a problem project is to fork it. In this case, it was an argument over the name according to Wikipedia, it's an argument over the name OpenSwan. So Paul Walters and the others, most of the others, created the project Libreswan. From there, things progressed, features were added, NSS became the crypto library, all these changes were coming through. By about 2018, several things have become clear. One was that Clips, which is one of the Linux kernel stacks, it was dying. Well, at least the developers of Libreswan were all rebelling and trying to get rid of it. Meanwhile, Netlink, which is the other Linux stack, it had evolved into XFRM, and it also then evolved into XFRMI, and it was starting to look like it would finally have feature equivalents to the clip stack. So it was all looking hopeful the clips was going to get dumped. But that would mean Libreswan would only have one kernel stack. Not a good place to be for a project. So in 2018 I kicked the old BSD code's tyres just to see what had happened. Only one wheel fell off. That's impressive. Didn't take much to get transport mode working, but tunnel mode, pretty weird. Something pretty weird going on. Turned out the problem wasn't actually the BSD code, it was the environment and the cools around it that had changed so radically that the way it was being cooled no longer made sense. So with that fixed, tunnel mode worked. 2019, Eclipse is officially announced as dead, going to be removed in 2019. 2020, Eclipse is actually removed, but still there are a few releases made that have clips because it seems to cling on for dear life. So now, continuing on into that 2020, we revived NetBSD, got it working. Very early code, of course, still trying to work out testing, which brings us to Ravi, Google Summer of Code student, and he's trying to get the BSD VMs running on our KVM test infrastructure so we can actually do proper interop testing of the BSD kernel stacks, end of Libreswan, and the other Ike daemons running on the BSDs. We want to make sure our code works with all of these. So enough of the history. Why was that important? Because when you look back at old code, it's good to understand why things were written the way they were. In the case of Libreswan, FreeSwan, the world changed. When the project was first started, everything was between home computers. Once someone got something working, it stayed up, never trusted it. And then in 2007, some company released an iPhone. And iPhones happened. Next thing, and ever since then, it's all been about VPNs, mobile phones, things that always crash, always reboot, net addresses that constantly change, connections that have to constantly be re-established. Very different workload, very different requirements. Of course, having a long history means you can have some old bugs. Here's a CVE. It was released as a CVE just because you're meant to do this. Anyone say they don't have any CVEs, treat them with suspicion. So this one was very late after things had been authenticated and all the rest of it, and you went to tear down an Ike v1 connection. You could potentially, in theory, maybe with an amazing amount of knowledge, possibly come up with a dud packet. The packet would just get dropped, which is why it says, this is incredibly low vulnerability. But it's there. The interesting thing to see is FreeSwan didn't have the bug. It was introduced in the first release of OpenSwan. And then, of course, StrongSwan, Libreswan inherited it. StrongSwan got rid of it when it got rid of the last of the Ike v1 code, and Libreswan turned it up and got rid of it last year. Just got to watch out for that. The other thing about history is whenever you're looking at things, you've got to remember you can't beat the laws of physics. These are off a laptop or a computer I got here. You can't get any faster. You might have 1,000 cores, still going to take 3 milliseconds to do that Diffie-Hellman calculation, then another 8 milliseconds to finish it off. So no matter what you do, you have to find 11 milliseconds to process a Ike and initiate a connection for Ike. You just have to find that time. Cores and everything help make it more parallel, but you're going to have to find that time somewhere. And this means, of course, when you're looking at performance, what you're not worried about is squeezing the last little bit of performance, obsessively inlining functions, obsessively using static structures, all this sort of stuff. What you're trying to do is get code that's understandable, and anything that could be a bottleneck is well under this 11 millisecond boundary. So let's see how we went. So Libreswan's performance. When FreeSwan was developed, everything was a linked list and it was obsessively worried about trying to conserve memory. Linked lists, yeah, 10 connections, 20 connections, 50 connections, 100 connections, 500 connections, 1,000 connections, all constantly reconnecting, starting to go run into problems. So with Libreswan, profile the code and find, as the number of connections goes up, where the bottlenecks are, and hash tables. Also, to just get RSA load down, cache the private key used when you're signing to prove you're doing your own proof of identity. You need to sign with a private key. It keeps an unpacked copy, which saves an RSA calculation. And there's a thread pool, so you can offload all the cryptography and run it on helper threads. Doesn't beat the laws of physics, but hey, 16 cores on a machine, cool, you can get through some things now. So we went from hundreds of milliseconds per exchange down to 30 to 60 milliseconds. That's with RSA. Still a lot of work to go, but we're getting there. More interesting thing for the kernel hackers is we're pushing through so many connections now that we're running into problems with the XRFM code in Linux. It's got linear algorithm problems. It can't. You go off, you say, here, add this SA, this child SA, and it wanders off into the weeds for a bit. I'm sure they'll fix that one pretty quick. So what else changed over the years? Testing. Testing evolved. Back in the 90s, what did you do? You wrote your function. If you're a good programmer, you wrote a little test program, but only you used it. You then shipped the library, and if someone came back with a bug, you re-enabled the test program, added a test case, rerun it, and ship the code again. Nowadays, the tests are always built. They're always compiled. And so we went through, found a hell of a lot of these little test programs and turned them all into unit tests and added them to the test framework. Made life a lot easier. Now, you need to change a parsing algorithm to parse some same string. There's a test case that just goes through and you're confident you haven't broken it. It refers to outpass. That's critical, Someone specifies some cryptographic suite, encryption, PRF and all the rest of it. You want it to keep parsing even when someone updates their version of Libreswan. So we put that into the test framework. The next bit of testing, interop testing. Can we talk to another daemon? Can we talk to ourselves? Can we talk to an older version? Always interesting results. So back in the day, it was in OpenSwan, there was UML testing added, so using user mode Linux. Bit of a dog's breakfast because you had to try and fudge things up with ports and all the rest of it, so it wasn't pretty pure, but it did help. And what it really helped with is lots and lots of test cases came out of it. You got a scenario, different cryptographic algorithms at each end, do they still operate, things like that. So all these tests came out of it, but running it was a pain, very much a specialized activity. So the framework around all the tests has been replaced by KVM. There's now some scripts, you just get a machine, Linux, and you install a minimal amount of things, KVM notably, and then you do a KVM install, spins up all the KVMs for you, and everything happens on the KVM. Libreswan's built on a KVM, keys are generated on a KVM, everything's on a KVM. So it's really, when it comes down to it, in theory, host agnostic. And in fact, if you want to beat the crap out of your KVM implementation, try running Libreswan's test framework. As an example, our testing machine is amazingly powerful. It's already a year old, 4 cores. Within it has 3 threads just dedicated to booting VMs, and then it's trying to run 6 parallel tests. And so in a 2-hour, 3-hour test run, it's probably done 3,000 VM reboots in other operations. So you've got leaks in your KVM code, you're going to find it. And based on history, we do find it. So, and again, as I mentioned earlier, we've got Ravi. adding BSD guests so we can start doing interop testing with that. The next step is again taking these tests. It's painfully slow to be booting up all these VMs, and so what worked was that Anthony, he's got namespaces, well, on Linux working, and so now we can use the same test files, but we can use namespaces instead of constantly booting up these VMs. Way faster, but you can't interop testing. You can't have a BSD machine talking to a Linux box and talking to a Windows box even, and we want to be able to do that still. So we're going to end up with both these systems running. More testing. FIPS rears its head again, and again, as I mentioned earlier, FIPS is a good indicator if someone's managed to get FIPS certification. They've probably spent some effort cleaning up the way the cryptographic algorithms are managed. So you go through the old code base and you find it's full of switches. I looked at a few of the Ike daemons that are around. Strong Swan, like Libreswan, instead of having switches and cases and bits of code, it has tables. It's table driven. You want to add a new algorithm? Add a table entry. Done. You want to delete an algorithm because it's no longer compliant for some reason? Delete the table entry. Gone. None of this wading through the code trying to find that little area where, you know, someone's pulled some narky hack because, I don't know, 3des has weird keys. All that code's been flushed out. So it's not FIPS that's interesting here, it's the effect trying to get FIPS certification has on a code base. So finally, we get to NetBSD and the NetBSD's backend PF key. So there's an RFC around. I've tried to read it. It actually confuses, I find it confusing. But what I don't find confusing is the IPsec library and the set key commands that come with it. Simple, easy, not a problem, easy to understand. So Libreswan, it's using, it just grabbed, it had a very old version of libIPsec, who knows where it came from. It pulled in, since it's trying to get running on NetBSD as a first case, it pulled in NetBSD's libIPsec and dropped it in, started using it. Nice and straightforward, simple interface. Did a bit of research, came with two interesting things. The first is NetBSD's libIPsec is still somewhat standalone. It was easy to pull in. FreeBSDs has been embedded. It's harder to pull, it would be harder based on what they've done. They've cleaned it up and integrated into their build environment and their userland environment. It would be harder to pull out. It's unfortunate because looking at the code base, FreeBSDs had a lot more love and attention than the NetBSD code base. You know, just in the short while I looked, I found a out of bounds access that's fixed in FreeBSD. I had to go through and stomp on good old W error warnings. People got rid of those, what, 10 years ago? And finally, doesn't matter whose version I used, I had to go and hack it so that I could get reroute the printf calls into Libreswan's own logging library so that I could actually debug stuff. But with that done, things fell into place pretty quick. Debugging, easy process. You run setkey, you see how setkey chats to use verbose, and you can see it chatting into the IPsec library. And then you go look at Pluto, you turn on cryptographic debugging, which means all that naughty hush-hush secret materials in there, and you compare the output. You know, setkey works, Pluto doesn't. You know where your bug is, Pluto obviously, and you also can see this is what the call should have looked like, this is okay, how I have to go and fix it. Spinning back to why tunneling didn't work, it turned out that NetBSD has a call to set up, first there's a call in the back end of Pluto to set up the SA, and then there's a second call, it's called e-routing, which tells it, you know, for these child SAs, this is how you route your packets. And for some reason, Pluto was calling set up an SA when it really meant to be doing an E-route. And once that was disentangled, things started to work. And the other cool thing about this, to really segue, is as a result of just this bit of work, we've identified chunks of code that are basically now dead. They probably did something useful once, but just no longer needed. And probably were never needed. So we're going to be doing some clean out, get things to work better. Anyway, that ends the talk, and apparently somehow we do questions. IRC, I don't know, we'll find out. And a good thing I finished now because it's about to turn dark.